In today's video, we'll be looking at electrophilic substitution of benzene, and specifically bromination. So first, an overview of electrophilic substitution. So benzene, our molecule up here, has a delocalized ring structure, and this ring structure is very stable. And this ring strongly attracts electrophiles, and electrophiles are species that seek electron-rich areas. And this delocalized electron ring is a really high electron-rich area, so it attracts these electrophiles. But benzene resists electrophilic addition. So in a previous video, we have looked at electrophilic addition. But with benzene, we cannot perform electrophilic addition because this would mean losing their stable ring structure. So this delocalized ring makes benzene a very stable molecule, and the molecule wants to be at its stablest state. And if electrophilic addition removes this, it's not going to happen. So it's going to want to maintain this ring structure, and that's where, to keep the stable delocalized ring, instead of adding an electrophile, they substitute a hydrogen for the electrophile. So this is where this electrophilic substitution comes in. So instead of adding an electrophile and just leaving it at that with electrophilic addition, we're going to have to substitute a hydrogen already on the benzene for an electrophile, so we don't disrupt the stable ring structure. So that's why it's electrophilic substitution of benzene rather than electrophilic addition. So we're going to be looking at specifically bromination in today's video. And this is when it's the substitution of a bromine atom onto a benzene ring. So you can see we have our benzene ring here, and we want to end with substituting a bromine atom onto it, maintaining this delocalized ring structure. So this is done by reacting liquid bromine and benzene with an iron tribromide catalyst. And this is done with heat. So specifically, if it asks for conditions, you need this catalyst and it needs to be heated. So the bromine that we mix with the benzene is going to be decolorized, and this is because our bromine molecule is going to be split, so it will no longer hold the properties, the color of the bromine molecule. And hydrogen bromide fumes will be given off, and we'll see how this is done when we look at the mechanisms and reactions. So now we're going to start with bromination, our reactions and mechanisms. So first we need to synthesize the catalyst. So we're going to need to get our catalyst here. So this is done by reacting iron and bromine. And then we get our catalyst. So once we have our catalyst, we realize that it is a halogen carrier. And this is really important in most of the electrophilic substitution mechanisms. So a halogen carrier are substances that can remove halogen atoms from molecules. And we'll see this now. So in our reaction mixture, our catalyst that we have now introduced interacts with some of the liquid bromine molecules that we've also put in there, and that is how we form our electrophile. So we have our bromine molecule that's in our reaction mixture, we have our catalyst that we've just formed, and because our catalyst is a halogen carrier, it is able to remove a halogen atom, remove a bromine atom from this bromine molecule. You can see here it now has 4 bromines. It's taken one from this molecule, leaving a really nice positive bromine electrophile, which we can now use for bromination. So we synthesize our catalyst, we realize our catalyst is a halogen carrier, and then it can interact with our bromine molecule to form our electrophile. So now we're going to be looking at the mechanism. So our bromine electrophile that we have formed through using our halogen carrier catalyst, and so our bromine electrophile nears our benzene ring in the mixture. And our bromine electrophile is attracted to this stable delocalized electron ring, because as we said before, an electrophile is an electron-seeking species. It seeks electron-rich areas, and this delocalized ring is electron-rich, so it is attracted to it. So then our electron ring attacks the bromine electrophile because of this strong attraction. So two electrons will jump out of the delocalized electron ring to attack this bromine electrophile. And this allows for a bromine electrophile to form a bond with this carbon. So because two of our electrons have jumped out to attack it, it is able to form a covalent bond with this carbon. However, this means that our delocalized electron ring is now disrupted, and this is because this carbon now has 4 bonds, so it's fully saturated carbon. This means that it can no longer donate any electrons to this delocalized ring structure. So we have disrupted this ring structure, and it's now a positive carbon. It's got a positive charge, and remember we're showing this hydrogen atom because this is a skeletal structure, and so technically we do have a hydrogen atom off of each of these carbons, we just don't show it, but on this carbon we will show it because it's important. So now this structure is now not as stable as before because we know that our electron ring structure is very stable. So because we've broken this, it's not as stable. So the benzene wants to regain this stability, so it wants to reform the ring, and it does a specific thing to do this. So to reform our ring, the hydrogen atom's bonding electrons attack the positive charge. So the electrons in this covalent bond attack the positive charge that we have now formed. And this leads to the hydrogen ion being lost. So it's given its electrons to the electron ring to reform this delocalized ring structure by losing this hydrogen ion. And now that our carbon has its 3 bonds back again, it is able to rejoin this structure, reform the stability. So now what do we do with this? Remember, we need to reform our catalyst, because remember, a catalyst is a species that speeds up the rate of reaction without being chemically changed by the end of the reaction. So we need to reform our catalyst. And so we need to react our ions together. And what ions are these? So in our first reaction, we have our catalyst with our bromine molecule. We form our electrophile and this ion here. And we haven't used that in our mechanism so far, so this is left over. And we have formed this hydrogen ion, and this is left over while we have our product. So we can react our leftover ions to form hydrogen bromide, which we can see in fumes, as we said in the beginning, and we reform our catalyst. So this is how bromination works.